por eso hasta el café me viene muy bien que sean las 9, a las 10:30 el café, que ya se sienta.
Esa cafetera la podemos usar todos mientras traigamos a cada uno su cápsula.
Sí, sí, sí. Está liberalizada. Fue donación de Antonio Hernán.
Solo tienes que apuntar tu nombre en la lista para tirar las cápsulas en algún momento de tu vida.
Ah, así en condiciones. ¿Y esas cápsulas dónde se tiran?
En el Mercadona.
¿Sí?
El Mercadona tiene una papelera de...
Sí, los dos creo además. Tanto, por lo menos el de Alcañiz seguro, pero creo que el Mercadona.
Bueno,
Australia is a strategic partner of ESO.
Yes, it is.
It would be nice if Brazil could follow the same example. They never joined in the end, right? They never paid because a minority of 4 people, the 4 horsemen of the apocalypse, as they're commonly known, they managed to convince the high spheres of Brazilian politics to avoid joining ESO because it was against their own interests. So they actually managed to damage the whole Brazilian astronomical community. Whereas Australia has been much more clever. But Australia developed OSPOS, right? And I think that was the first interaction between Australia and ESO.
It was, and OSPOS actually was built by the AAO way before I joined, but yeah. And I think many of us are hoping that this strategic partnership will turn into full membership of ESO in due course, but yeah, we're working towards that.
That would be fantastic.
Okay, I think we can start already. So thank you for being here. Today, the seminar is going to be given by Nuria Lorente. Despite the Spanish name, she has been raised in Australia, although she speaks quite well Spanish. In her career, he did the PhD in Sydney University, and then moved to Manchester and stayed some time in the UK. Then moved to the US to work in ALMA, and then she switched ranges and finally came back to Australia, to Macquarie University. And today she's going to talk us about the research software and data engineering. So whenever you want, Nuria, all yours.
Thank you so much. Good morning and buenos dias. Thank you to Juan and Mohammed for inviting me today. I'm really happy to speak with you, although I'm sorry I can't be there and do it in person. That would have been brilliant. As Juan said, I'm at the AAO, which is part of Macquarie University. At the moment, I'm co-head of the Research Data and Software Division of our department. And today I'd like to talk to you about the work that we do at the AAO, and particularly within RDS, and how it touches almost every part of astronomy research. So as the title says, what is research software and data engineering, and why should you care? So just very quickly, particularly for those who may not be exposed to software engineering, what is it? We know that it's not just writing code. It's taking engineering principles and knowledge and applying those to problems that end users might have. It does involve programming, but it also deals with the design, development, testing, maintenance of software. A very essential part of this is requirements capture and analysis, which if any of you have worked with software teams, you would have spent quite a deal of time speaking with engineers and articulating exactly what it is that you want your application to do. And a lot of testing and improvement and maintenance of the software, because requirements change over time, hardware changes over time, and the well-known software development cycle, which just goes round and round, and you feed it talent and funding, and out comes better and better software solutions. On the other hand, what is data engineering? It's a term that is being used more and more, and certainly in industry, it's a rapidly growing area. It's again applying engineering principles to dealing with data, particularly large data volumes coming in at speed. So it's the practice of designing and building data systems for collecting the data, storing it, analyzing it. And often data engineering requires software engineering to go hand in hand. So really our data engineers are software engineers as well, by and large. So for large amounts of data, we need to ensure that by the time it reaches the astronomers, the analysts, that it is in a usable state. And depending on the application, we either use bespoke tools that we write ourselves or off-the-shelf tools, or more often than not, a combination of both. Very importantly, a data engineer is not a data scientist. A couple of our data engineers overlap into data science, but on the whole, they are not. An astronomer, on the other hand, I would argue, is a data scientist. And often a data scientist who may also dabble in software and data engineering, depending on their background and interests. So bring those two together, and you have research, software, and data engineering. So the engineering disciplines working within a research context. Our software and data engineers often, but not always, have a background in research. We also have engineers who are career engineers, also mathematicians, all sorts of expertise that come into the team. And it is a dedicated career. And for example, we have dedicated conferences for the disciplines, and I'm mentioning ADAS here because if any of you are interested in astronomy software systems as a subject, I encourage you to look up ADAS, and we are meeting in the US in a couple of months in November. So I have here all large research infrastructure projects have engineers in their teams. If they don't, they really should have. And as our projects become larger and more distributed, we are finding that it is not a nice to have, it is crucial to have this expertise. So just a little bit of background about the AAO. Some of you may be familiar with that. We mentioned AusPos just before. So the AAO was founded in 1974 to build the Anglo-Australia telescope. And it operated for many years and became well known for building instruments for optical telescopes. In 2018, the old AAO was split into two parts. The telescope and the telescope operations was handed over to a consortium led by the Research School for Astronomy and Astrophysics at the Australian National University. And the instrumentation side of the AAO became Australian Astronomical Optics, we're still called AAO, in the department, in the Faculty of Science and Engineering at Macquarie University. So we are, half of us continue to be the same people, the same AAO. In fact, we haven't even moved buildings. My office moved one floor up, but that was all. And we continue to do what we have always done, so built precision instrumentation and hardware, and dealt with research data and software. And that now is the two streams that we have within the department. Our team, and this is our team, Simon O'Toole and I co-lead this excellent team of engineers and scientists. I won't talk about it, but I encourage you to look into the collaborative leadership model, because certainly I find it works very well. It's not novel. Lots of companies do leadership by collaboration, and I find it's a fabulous way to get a team working together. Our team, as you can see here, I don't know if you can read their job descriptions. They are a mix of ex-astronomers, software engineers, data engineers, IT professionals, and a couple of instrument scientists. Our mission within the RDS team is to facilitate science and research across multiple disciplines by building bespoke tools, infrastructure, and services based on the best technologies available. Note that I say research across multiple disciplines. I will talk about that a little bit later. But of course, our home is within astronomy. Our expertise is across software design and engineering, data management and engineering. I've mentioned those already. DevOps, so development and operations, and user computer interfaces and user interface design. Since joining Macquarie, we have expanded the teams that we work with. We work with anybody who needs data management, particularly if they need bespoke applications. So not just spinning up a database, but actually writing a platform or writing ingestion tools. We also work with teams that need some help with their collaboration services, web applications. Every project needs a website, and really most often researchers and their postdocs and their students don't want to be spending their time doing these sorts of things. You want to be doing your science, and so we take that burden, which for us is a lot faster and easier to do because we do many of them. We don't just work with Australian teams, we also work with teams internationally. And as I said, mostly astronomers, but we are expanding into other disciplines, which is very exciting. And these are some of the organizations that that we work with. Those that you will be most familiar with are probably ESO, the AstroPi team, various telescopes, the Vera Rubin, and so on. So to give you a little bit of a look at our landscape of projects, this is what we have at the table, on the table in the last couple of years. Our two flagship projects are Data Central, which is a science platform, and ESO Pipelines, which is the development and maintenance of data reduction pipelines for ESO's VLT. I will say a little bit more about those two a little later on. But within astronomy, you can see that we contribute to several instrumentation projects, as we have always done. So this is hardware control, data simulations, data reduction software, and so on. We also are doing data engineering for the ANU's 2.3 meter telescope upgrade. This is a telescope on Siding Spring Observatory. Also similarly for the University of Newcastle's Solar Observatory. And we've started working with the Vera Rubin Observatory on some very interesting data management and data engineering projects. And joining a university has brought us into contact with a broader expanse of researchers. And with that, the realization that they often have similar data and software problems that astronomers have, and they can benefit from the experience that that we have coming from astronomy. So, for example, this Oracle is an early childhood education research project. They deal with sensitive data because it's data about children, and they needed to have a platform to collect these data and set up a system so that researchers could look at the data that they had authorization to see, but possibly not the whole data. Sometimes data needs to be anonymized, dealt with in some other way. We also developed an application for the archaeology department to allow them to take data using mobile devices synced to a central database. So that's quite a different field, but it's still the same problem. We're taking data, we want to not lose it. And these days we want to walk around and take the data on our phones. So that was a very interesting project. Then looking into the future, we have a mix of astronomy projects. You can see here ESO pipelines. We're waiting to see if we will continue this work over the next 5 years. And also looking at, we're speaking with departments in the health sciences and medicine and talking about how we can bring our expertise to help them. So you'll see there the Center for Emotional Health. There's dementia research, the Australian Hearing Hub, hearing loss research, and so on. At some level, all of this is just data, which makes it possibly sound a little bit trivial. It's not, it's important data to the researchers, but from our perspective, the same principles apply. So I might take you on a brief overview of our astronomy projects. As you can see, many of them are interconnected, which is not surprising. Collaboration and interoperability between the services that we provide and the organizations that we provide them for is quite important. So we run Data Central, which is an e-research platform and data archive based here at Macquarie University that facilitates cutting-edge astronomy research. We provide web-based tools and archive functionality for researchers so that they can explore the data, collaborate with each other, and make new discoveries ultimately. And our goal is always to help the smooth and successful execution of research projects and the management of between teams and researchers. So that's Data Central. So we have two key goals within the Data Central platform. One is the goal of any archive save the data, and the second is to help research teams. We support a couple of research centers, which you can see here. And in terms of the data, we support a large number of projects. I don't know whether that is too small to read, but Hector, Galar, Devils, Sammy, some of you may be familiar with these. So we have all sky coverage in multiple bands. We have millions of spectra. One thing that we're quite pleased about is that we were able to resurrect, if you like, many small lost data sets of AAT data. And the data is not just sitting in a database, but the science platform allows you to search for it, to cross-match it. And we also allow a layer of privacy to, for example, to allow you to look at proprietary data, which might be useful, for example, if you're referring a paper. I mentioned teams. A boring but important part of doing research is setting up your team. So setting up a cloud space, setting up a wiki, setting up a website, where to put your documents, mailing lists, all these sorts of things. And so we have data central teams that does that for you. And what you get, as well as these various spaces, you also get authorization for the data that you have put into the data central archive. So for example, if you ask us to ingest your survey data and then tell us, well, my team are, actually, no, you don't tell us who your team are. You tell us, I would like to set up a team. We set up a team for you. You put in there who your team members are, and then they have access to those data in a private and secure way. Then we can provide virtual machines to on which to process the data, and so the science platform is a seamless way of the whole team being able to collaborate on the data without any of the individual scientists having to know how to set up a data server or spin up a database, which I imagine you generally don't really want to be doing. So this data science platform is part of the we're part of the IVOA Alliance, so the International Virtual Observatory Alliance, and the reason for existence of the alliance is to share data between facilities, and really what they do is they set up standards to allow facilities to do this, and to allow us to apply the fair data principles to our astronomy data. I encourage you, if you're not aware of the IVOA, to have a look at their website. Some parts of it are a bit dry, but they provide some of the crucial tools that underpin a lot of the things that we do every day without really thinking about it. I mentioned the FAIR principles, and these are important principles for scientific data management. And it's about data being findable. So how easily can your data be discoverable? How easily can it be obtained, accessible? How easily can be compared to other data, interoperable? And how much can your data be trusted? So can it be reusable? And ensuring that our data management adheres to this will then make your data more valuable, easier to find for all researchers, easier to combine and integrate with other data sets, and easier for somebody to come back and use the data that you have taken today in a paper that they will be thinking about in the future. So I'd now like to talk a little bit about the ADAX project that we are part of, and I believe that this project is what piqued Mohammed's interest in having me give a talk. So ADAX is the astronomy data and computing services. It is a national initiative funded through the Astronomy Australia Limited, which is our astronomy funding body in Australia. And the funding comes from the National Collaborative Research Infrastructure Strategy allocation, so NCRIS. What the ADAX program does is it provides software engineering, development, consultancy, and training to the astronomy community. The idea is that astronomers want to be doing astronomy. They don't want to be doing software and data engineering. And as our telescopes, our instruments, and our data sets grow, you really cannot do both well. And so the idea is that for some things, that work should really be done by a software and data engineering group, much like ours. So this initiative has three nodes, where one of them at Macquarie University, but Swinburne University and Curtin University are the other partners. And broadly speaking, we form a group of professional research software engineers with expertise covering scientific computing, high performance computing, web development, scientific databases, cloud and microservice architectures, and scientific visualization. So we have a suitable mix of computationally skilled astronomers, traditional software engineers, and project management professionals. It is super important that this group has good domain and community knowledge. We also have various certifications in user-centered design and agile methodologies, which really is what many of our groups use on a day-to-day basis anyway. So there are three components to this program. The first one is training, which is really important to teach astronomy students, early career researchers, how to write good Python, how to use the various tools of software engineering that they will come across in their careers. This is mostly done by our colleagues at Curtin. There is also a significant component of supercomputer software support, and this is mostly done by our colleagues at Swinburne. So this is code optimization, parallelization, the TAC, the time allocation committee for the supercomputer, and so on. And then the last one is the merit allocation program. And this is split mostly between ourselves at the AAO. So we do a lot of the astronomy data and software engineering, and Swinburne University, who do sort of both more general software and also supercomputer specific things, so GPU programming and so on. So this merit allocation program, what that is pretty much like applying for time on telescopes, except that what you're applying for is software engineering, data engineering time. So you're applying for time from a person who will come and try to solve your software and data problem for you. And the way that this looks is you're invited to submit an expression of interest, detailing what sort of help you will need. Then somebody from the group comes and has a chat with you, and together you estimate how many weeks of engineering time you will propose, and then you put in the full proposal. It goes to a time assignment committee, just like it would if it was telescope time, and then the proposals are ranked based on scientific priority, and also whether it's technically feasible. So this has been going since 2017, and it has worked very well so far. All three parts of it, the merit allocation, the training, and the supercomputing, have been working very, very well. Ourselves at Macquarie, we have joined this program recently, and we have been doing quite a few projects, and I'll just outline a couple of them to give you a flavor for the sorts of things that we do. So the first one I'd like to mention is called SimSpin. Well, SimSpin actually was software written by Kate Harborne for her PhD thesis. It was a software written in R, and it's a tool for generating mock observations of simulated galaxies. So that's fantastic. She had this excellent piece of code in her drawer. But what she asked for was for some engineering time to make this much more accessible to the general software community. So Liz Davis, who's one of our senior software engineers, set up this web application using Docker. She had was building multiple images simultaneously, and I think I've missed. Okay, somewhere I've deleted part of that slide. I apologize. You can go and have a look at SimSpin in Data Central. This is really a front end to an R software that an astronomer wrote. There we go. This is what the front end looks like. You can see that if you go to the website, and it just provides that extra level of usability and accessibility for Kate's very, very good algorithms, which would be far less useful if they were just sitting on her computer and she had to send the R package out to people who maybe don't know how to run R programs and so on. The next one I'll quickly mention is the Veloce data reduction software. So this was proposed by the Veloce PI, Chris Tinney, at University of New South Wales. So Veloce is an IFU fiber cable fed high resolution Echelle spectrograph, which is on the AAT, and its science is planet search. The data reduction software were a number of Perl scripts written by Chris, and the request that was put through was, can somebody please help me with these scripts to improve the usability, the maintainability, particularly extensibility, and the robustness. So what we did there is Tony Farrell, our technical lead, had a look at the code, started by taking Chris's scripts, put them into a Git repository where they could be made available, removed the original developer dependencies, so all those bits in the code that say, /home /me, as a first step to making it more extensible and usable by other people, got it to build and to run, and then did a code audit. And the result of the project was a proposal for improvement, so for the next stage. And the expectation is that Chris will now go back to the time assignment committee and put in a second proposal saying, okay, so this is what the recommendations were. I'd now like some more engineering time to do the following things. And again, this is another example where some code written probably while up the mountain commissioning the instrument that Chris wrote is now being turned into a product that will last the length of time of the Veloce instrument, because at the end of the day, the astronomer doesn't want to be sitting writing software. He wants to be taking the data and doing the science. The next one I'd like to quickly mention is AAO Muse Pipe. So what this is a Python package to do the data reduction from the ESO's Muse instrument on the VLT using PyCPL and PyESO-Rex. Now, this came to us as a Python code written by Eric Emsellem and others called PyMuse Pipe. we were asked to simplify a lot of the housekeeping of this code, and we simplified and extended the functionality that was already in PyMusePipe. The code was a little bit dense. It operated a little bit like a black box, and so they wanted something that was a little bit more astronomer friendly without the steep learning curve and without the time investment that would need. So what we did is, because I will say later on, because we have developed with ESO, PyCPL and PyESO-Rex, which are wrappers to the ESO's CPL library, we were able to take those tools and massage PyMusePipe into a much better form, so that it was a lot more user-friendly. So the aim of this was Jesse van der Sand, who plans to use it to reduce data from the Gecko's large ESO program. And then finally, I'll mention Image Ninja. Every instrument that we have ever built anywhere, I imagine, has a need for a data simulator. And too often, a new data simulator is written every time that we create a new instrument. So Image Ninja is a framework to allow the instrument teams to create a simulator by setting up a structure and allowing the instrument scientists, or most probably the software engineers, to write functions that you slot in, for example, to add cosmic rays to a perfect data cube, or to add detector noise, or whatever else. So this was a request by Trevor Mendel. He came to us with IFS Sim, which was written by Peter McGregor. This code runs, in fact, on a machine. They cannot get it to run on a different machine, and they wanted some help to get that sorted out. So we looked at the code. Rather than trying to fix this code, which is quite old, the original developer is long gone, and inspired with previous work that we've done on SpecSim, and others have done on Maisie and PySpecSim, we went a step further and went back to, okay, what do we really need here? And created this simulation framework. So the plan now is that this Image Ninja will be used for multiple instruments, including Mavis, which we are currently building. So back to our interconnected Net of Things. I'll next mention data reduction pipelines a little bit. So over the last almost 5 years, we have been working with ESO to develop and maintain just over 20 of their data reduction pipelines for VLT instruments. We've done this in partnership with the Australian National University, so our software engineering colleagues there. It's a 5-year project that we're coming to the end of, and we have just applied for the next 5 years of work, which I hope to find out about in the next couple of weeks. So just to give you an overview, there we are. So these are the pipelines that these are the pipelines that exist. The ones on the left with the Australis logo are the ones that we have been maintaining. The ones on the right are the ones that the ESO team maintains. And a couple here we work on very much as a collaboration. So we maintain the pipelines for both extant and decommissioned instruments, because of course the data remain in the archive. And so if you want to download some Symphony data on your new M2 Mac laptop and process it, the ESO software needs to run on an M2. So this maintenance is ongoing, as well as putting in new features as the ESO scientists and the community request. We've also been working on a lot of testing, so automation of the unit and regression tests. And part of that means that earlier this year, some of these instruments no longer need our support. So the ESO team spent a great deal of time last year increasing the automation of regression testing. And so now all of these decommissioned pipelines are mostly dealt with automatically, which is nice because it leaves us more time to work on tricky things like Muse and telluric corrections and so on. So where have the 5 years gone? I think I estimated we've put in something like 22 full-time equivalents over the last 5 years. The time's divided into some major projects, which over the last year or so have been related to quality control in Paranal, with ESO's soon to be released EDPS data flow, new data flow system. The quality control work is becoming a lot more automated, and so that means that the instrument pipelines need to do some of the things that used to be done in sort of hand-driven scripts are now done automatically by the data reduction pipeline. So we also have main development projects, which are projects that take from 2 weeks to 6 months. And these are projects that go to a committee who decides which ones are going to be done in the next quarter. The proposals are put in largely by ESO scientists, but also some of them come from the community, and then they come to us once ESO have prioritized these. And some of the things that we have done are related to telluric correction tools. If you use the VLT, you probably know MolecFit and have used this, and we've spent some time bringing that functionality to the individual pipelines so that you don't need to run MolecFit separately. Also, Vizier has had some general improvements. The high-level data reduction language has had some work to improve infrared detector persistence corrections. Some work on X-Shooter and FORS, and then a fair deal of time every year is put towards the coordinated Paranal and public releases of the software. So once a year, all of the pipelines are re-released with new versions of the operating systems. Every time Mac brings out a new version of Mac OS, we make sure that everything works on the new hardware. and fix things when that goes wrong. I mention the Macs because they are perennially the cause of grief. The Unix systems that we support are less problematic. And finally, there is routine maintenance. So you as an ESO user might find a bug in the data reduction code and report it to ESO through the user support group. That then goes into a JIRA system of reporting tickets, and then eventually that comes to us in Australia to resolve the problem. So I mentioned in passing PyCPL and PyESO-Rex. The VLT pipelines are written in ISO-C, and they are underpinned by the ESO pipeline library, which was written in 2003. And it contains a lot of the basic functionality that you need to write a pipeline that you don't want to rewrite. So things like how to read, how to read a FITS header, how to look at, how to pass in parameters, all sorts of general things. It is a super useful library. It is very efficient. Because it's been around for 20 years, it's robust, it is well understood. The problem is, how many of us comfortably write in C? I do, but how many people in the community? Most people in astronomy like to write in Python. And so we were asked by ESO to implement Python bindings for CPL so that people could execute the current data reduction pipelines from a Python environment, which is what most people use. It means that people can make use of that well understood library. It also means that you can use that to write data analysis tools that you would normally write in Python, taking in the product of the VLT data reduction pipelines. So it's sort of a natural place for the software to go. So as I said, CPL is generic processing functions. There was a Python CPL written for Muse, but it was just for Muse. So what we're doing here is extending that to the entire of the functionality of CPL. We do this by using an off-the-shelf package called PyBind 11. And what it does is it automates some of the binding work. So PyBind 11 takes C++ types and data structures and so on and exposes those to the Python environment. Now, of course, I said CPL was written in C, not in C++. So we've had to write a thin C++ layer to sit between the CPL and the PyBind 11 library. That actually works quite well because although CPL was written in C, it was written with an object-oriented mindset. So a lot of the things map very well to C++. Why should you care? Why am I telling you this? Apart from, I get excited about it because it's what I do, and the team have done a fantastic job. The reason you should care is first because you can use it to run instrument pipelines from Python. It's yet another tool in the astronomy Python ecosystem, which these days is very, very rich. And it incorporates that CPL into your post-processing Python code. But also, you can use it to prototype data reduction recipes for new VLT instruments. And this is what we're doing with Mavis. It just so happens that some of the team that is working on the ESO pipelines is also the team that's writing the data reduction system for Mavis. And so for us, that's a very natural next step. We have pre-released the PyCPL many months ago now. So version 0.9 is available. Version 1.0 we expect to be released in probably October. And Anthony Horton wrote a rather good demonstration of PyCPL for the ADAS meeting last year, and you can access that here. And the next step after PyCPL will be to bind the high-level data reduction language, which has algorithms that are much closer to what you would think about. Also binding that in Python for exactly the same reasons. So what else is has this project given us? It's allowed us to collaborate with ESO in lots of other ways that are not just the code, in improving the efficiency of the annual releases. We've collaborated in testing across all the different hardware and operating systems. We've also had a couple of workshops on topics that are of interest to both groups. In 2021, we had a very interesting workshop on containerization. And last year, we talked about pipeline services of the future. So how are ESO thinking of doing ELT pipelines? What have we seen in other projects that we're involved in? What synergies can there be there? So synergies with the ESO archive, as I say, but also PAWS, which is one of our projects. PAWS stands for Pipelines as a Web Service. And the idea there is not to have to download the pipeline onto your laptop and process things there. If you've observed with Muse, you will know that that's not actually possible. Yes, I can see somebody nodding. So what we do there is we have a server dedicated to running Muse, and then we will provide a web interface so that you don't even have to upload your data. We have we can access the ESO archive, or you can access the ESO archive through our science portal, and set up the pipeline to do your data reduction, and then send you an email when it's finished. And at that point, you download the data products. So that's still in flux. This is currently working not for ESO pipelines yet. It's working for 2D-FDR, so AAT data and the 2D-FDR data reduction system, but it will in future work for other instruments. I'm aware that I'm running out of time, so I'll very quickly just say we are working with the Vera Rubin Observatory. We are part of one of the independent data access centers in conjunction with Swinburne University. So the data will be hosted at Swinburne, and we will be providing the software effort. This is super exciting for us. I was going to say I can talk about it afterwards, but that's only really the case if I was there. So just to finish, let me tell you a little bit about software and data engineering beyond astronomy. When one of the great things about joining a university was to expand beyond our silo of astronomy into other research fields. And we now work with a range of researchers from other disciplines, which I find super fascinating, from the perspective of how many of the problems that we have are very, very similar. And the issues, whether technical or sociological, that we have in astronomy, we see in other research fields as well. I mentioned the Oracle early childhood education research. The main thing there from our perspective, from the data perspective, is allowing granular control of access of the data and providing them with the capability to do data analytics. This has been going really, really well. We love working with this group, and they're doing really interesting and important work in their field. And just to summarize, I believe that research software and data engineering does play a key role in making sure that researchers can acquire their data, reduce the data, process it, analyze it, share it. And in our group, we work with researchers in astronomy and other fields to enable and improve research, which at the end of the day is what we all aim to do. And we're always looking out for interesting new projects to collaborate with. So if you're interested, give me a call and I'll be very happy to chat with you. And I will leave it there. Thank you.
Thank you very much, Nuria. Very, very nice talk. I think Mohammed has a question.
Yes, thank you. Thank you very much, Nuria, for presenting this nice summary of what you're doing in AAU over there, this really interesting initiative. So my first question is about the research software engineer's profile. How do you, is it similar to a postdoc, an engineer? Because they also need, as you said, a background in the domain in astrophysics. So, and then, for example, just on the technicalities, like is the salary similar to a postdoc or an engineer, the career path? Because to attract someone with background in astrophysics, you have to make it attractive for them, right? Like the career path, can they become the department head? Is it permanent or temporary? These kinds of things is really curious, and I'd really like to know how you've addressed the problem in AAU.
You're asking the perfect questions, because that is a huge concern. So first of all, attracting people. In the past, we've been able to attract people because we had we allowed people to have flexible working lives. You know, they didn't have to be at the office 9 to 5. They could work at home on some days and so on. Of course, post-COVID, we're no longer unique in this by a long shot. And salaries, industry will always pay more, always. We are not really competitive with that. And last year, our team lost 5 people, and several of them went to higher paying jobs. And I don't mean higher paying by a couple of $1,000s. I mean, you know, more than $10,000 or $20,000 more. So that's a perennial problem. So what we try to do is, first of all, you know, we do really interesting work, right? We are not asking engineers to make speed cameras work better for the police, right? We do research. We're not writing software for supermarket checkout registers. You know, all these other things are important, but what we do is exciting. And that is our big draw card. Our second thing is we try very hard to provide a really positive working environment. And I think, and in some ways, that is one of my primary roles, is to make sure that our team has everything that they need to do their best, most creative work. Not all of our work can be super exciting. All projects have some donkey work, right? But it's that juggling to ensure that, okay, you're doing something that's not so exciting, but it's important on this project, and I'm going to make sure that you are recognized for that. And the next project, you get to do something a bit more interesting. So I think a lot of focus on what the engineers need. You asked about career path. This is a problem, and it's something that we are currently working on. And in fact, our director of our institute, Mark Casali, is working on within the university. Engineers within our university are not academic staff. They are professional staff on a different salary scale with different conditions, and not permanent jobs. And of course, that's not sustainable if you're wanting to build a group that is best in its field. So this is something we're working with the university. The university recognizes this, but university processes are slow going. And in the meantime, we try to provide a promotion path in other ways. By taking, okay, so if I want to promote somebody, they have to apply for another job. They cannot just be promoted. So we try to do that in a way that is actually about their development. And in fact, I do believe that if somebody works in our group for 10 years, and we have never talked about how would you apply for your next job, how would you do a job interview, then I'm failing in my job. Because when my engineers leave, I want to make sure that they are taking a leap into their next challenge well prepared to do that. So I try to turn it around and say, okay, I'm sorry, you're going to have to apply for the position of the next level in a formal way. It's not guaranteed because all our applications are open to everybody, but let's look at this in a developmental sort of way. You could argue that that it's easy for me to say that because it's not my job on the line, but my job's not permanent either. So, so yes, it is a problem, and Mohammed, you've hit right on the head the biggest concern that keeps me awake.
Okay,
apart from the funding problem, which is also always a concern.
Yes, thank you very much.
More question, Alessandro?
Just piggybacking on this a little bit. When you introduced the team, you briefly mentioned what was it, coordinated leadership, something?
Yes. Mm-hmm.
Could you
leadership? Yes.
Could you expand on this?
Sure. So most of the teams within the university, they have one lead, and we had that in the past. Our previous head of group was Katrina Seeley, who is now executive director of the faculty. And Simon and I so he led the data and IT team, and I led the software team. When our previous head of group left, we were asked, what do we do? Which one would you like to compete for the position, right? And we had quite a few discussions and actually realized that this model, where rather than having one person at the top and then a pyramid, a model of collaborative leadership actually would suit what we're trying to do a lot better. And what that means is, both Simon and I can stand up in front of a meeting and say, I am head of the research data and software team, and that is correct. Because what we do in collaboration. So if I make a decision, Simon and I don't have to agree all the time, and we don't have to ask each other all the time, obviously, for a lot of the important things we do. But rather than a combative model, which many setups are, we bring different strengths to the team. And what we're trying to do with our team is actually to set up a team that collaborates naturally. And I feel that if the leadership is collaborating, then that almost naturally gives that example of you must collaborate, because this is how we do things here. It is not my software, it is our software, or idea or paper or whatever. It's worked very well. I think it's one of those things that if you get two personalities that work well together, it works well. I imagine it doesn't work for every team, but yeah, for what we're trying to do, it does work well. If you have a look, there are quite a few technical companies in industry who have opted for this model as well. And what it means is that you always have somebody at the same level as you who understands what you're trying to achieve, but is able to say, hang on, that's not right. Or, you're getting too emotional about that project. Or, I don't know, did you forget to think about this other thing? I think maybe because we've both come from astronomy, where collaboration happens on ideas and on papers, it seemed quite a natural step. But it works quite well. Yeah, we've been doing this now for maybe 18 months. So I don't know, maybe ask me in a couple of years if it's still working well.
I'll send you an email. Can I ask another thing?
Yeah.
If I want to use data center for all the infrastructure that you commented, I assume I have to register somehow.
You can.
Can I register?
And yes, you can.
Based down under. Okay.
Absolutely, yes. You can go to Data Central and click on Set up an account, and you register and play around with it, have a look at it. If you want to chat about what we can, about what it offers, because of course if you were here, I'd come to your department and we'd sit together and say, okay, so what are you looking for, and what sort of data do you need? But yeah, have a play, and we can have a Zoom to talk about it.
Good luck. Yeah, thanks.
Okay, more questions? I have one about the.
Mohammed just raised his
hand. Okay, Mohammed, go ahead.
Thank you. So another question that was interesting for me is like for the shorter projects that were less than 6 months. So imagine you help a team develop something, and then the job is done, the 6 months is finished. And then in the future, say like in a few months, bugs are found, or this Mac releases a new operating system. So how do you, what's the procedure for these kinds of supports after the official requested period finishing?
Yeah, that's a really, really good question, Mohammed. So at the moment, if you get a new Mac and suddenly your code doesn't run, you need to put in another request for time. So to go through the time assignment again. In reality, you probably send an email to the engineer who was working with you, and if you can sort it out very quickly, you get it sorted out. But if it's something that requires, a couple of weeks of work, you would go through the process. But we are speaking with within the ADAX group to see if we can find a way of setting aside a small amount of effort each semester for exactly that sort of thing, for maintenance work of previous projects. Because of course you do this work and then software can never be stagnant, because as soon as it's stagnant, it becomes old and eventually unusable. So yeah, we are working on finding a way of setting aside that time, because it's super important.
Exactly. Great. Thank you.
I have a very short question. Is CPL and ISOREX is going to be the base of ELT's new instrument reduction pipelines, or
No. Sorry.
No. Or if there is going to be a fundamental change in that aspect.
So at the moment, PyCPL and PyISOREX are to be used for prototyping only. So if you look at the at ISO's 1618 document that gives all the rules about how to write data reduction systems for new instruments, it still says the pipelines and the recipes need to be written in ANSI C. However, ISO are writing a new data flow system for the ELT, which is called EDPS. And my understanding is that they will be doing a pre-release of that to instrument consortia, at least. I'm not sure if to the community at large, in the next few months. So I believe that before the end of the year, we will see EDPS, or at least an early version of EDPS, so that we can have a play with it as a community. And so in the longer term, that will form the basis of the pipelines. I don't know whether eventually we will be able to write pipelines in Python using PyCPL. I'm not 100% sure that we will want to. Maybe writing parts of them in Python and the underlying number crunching still done in C. But certainly for now, PyCPL is only for prototyping in an ISO context. I mean, obviously, if you're using one of the ISO pipelines and you have some Python code to do some post-processing, then of course it makes sense to use it in there.
Okay, thanks. I think Mohammed, the last question.
Yeah. Sorry, Nuria. This is a really interesting new concept. So I'm curious, how do you measure success in a project after it's done, especially to the funding agencies of you? So for example, like for telescopes and observing time, they usually count papers. They usually compare, like, Keck had this many papers, BLT had this many papers. But do you also do that? And yeah, can you explain how you encourage the funding agencies to continue funding you based on what you've already done?
Yeah. So we don't count papers at this stage. Although I am seeing, particularly at conferences, people mention, the software for this was done using effort from the ADAX project, which is great, because it means that people get to know that this this service exists, that this project exists. I think we will have to find a way of showing the funding bodies that that this system works very well. At the moment, it's done in combination of talking to the proposing scientist and getting feedback from the engineering team as to whether both sides felt that it was a success. I mean, obviously, if the scientist is able to walk away with the initial problem solved, but there are many projects that start with the astronomer asking for a particular thing, and then in the process of doing that work, everybody realizing, including the astronomer, that what they really wanted was something else, and the project taking a bit of a turn. So that's not always a great metric. Did you get what you asked for? But I agree that in the longer term, we need to have a better accountable metric, although these are not always, they're not always great, because sometimes you get what you measure, right?
Exactly. Yeah.
So yeah, it's a slightly tricky problem.
Exactly. Thank you.
Okay, thank you very much, Nuria, for your talk.
Thank you so much. It was a pleasure speaking with you, and I hope that next time I'm in Spain, I can drop by and say hi in person.
Sure, come here and meet us in person. You're very welcome. Okay, thank you.
Lovely. Thanks all. Have a great
you.
day.
Bye-bye.
Thanks a
Bye.
lot. Thanks a lot. Bye-bye.